Okay, welcome everyone to this continuation of quantum topology. So today I will tell you about essentially I'm trying to tell you what a quantum invariant is, because quantum topology is essentially about quantum invariants. It should be a functor from a topological category to an algebraic category, and the main point it will be that you can actually construct the algebraic categories explicitly. But before we can do that, first of all, I need to explain to you the usual kind of not target category, this usual source category that we like to study, because kind of knots is what we have in mind, but it's not quite what we can do on the algebra side. On the algebra side, we can do a slightly more sophisticated object, and we'll do that today. So it's called a ribbon. We'll see what that is. So these are the twists. So Reidemeister 1, whatever you want to call them. So you have an object X, and you just put a crossing on itself, essentially. And you can do that in two different ways, like right or left, right? So right or left and on X, and it just cross over. And both of them have, again, a different kind of an inverse, if you want, when you flip the crossing over. But we have this right twist and the left twist, yeah? And you can do that in any braided pivotal category, because braided, you just have a crossing, and pivotal, you just have caps and caps, so you can just do that, yeah? So every object admits right and left twists. And this is literally what it is, like kind of a curl defined from the braiding in the caps and caps. So somehow you naturally, in a braided pivotal category, you naturally get to these things, yeah? In a braided rigid category, you can write down these type of objects. So braiding plus duality naturally produces kind of a Reidemeister 1 move. And braiding itself, of course, produces the Reidemeister 2 and 3 move. So somehow the little last thing we need to sort here is how the Reidemeister 1 move kind of behaves with this general concept of a braided, rigid, whatever you want to call it, category. I'll give it a nice name in a second, right? You have braiding and you have caps and caps. Okay, what's going on? I can move it. Very good. 3 versions of Reidemeister 1. Turns out you need 3 versions of this. And I called them, or they're called, the classical Reidemeister, right? Not satisfy that thing. The 5H2, not satisfy 5H2. And then I have the ribbon equation, which is a bit weaker. Of course, 5H2 implies 5H3, but the converse is not true. I'll show you a nice example in a second, making it clear what the ribbon equation is. It's equivalent to the thing on the right-hand side, but don't worry about that. So it says the left curl is the right curl, right? So the first thing says the left curl is the identity, is the right curl. And the second thing only says the left curl is the right curl. Weaker thing. And the final one is called the framing. Don't worry about it too much. I'm not going to dwell on it too much, but it looks like this. The curls invert one another. And it's not difficult to see that 4 implies 3, right? So 4 implies 3 implies 2. But not the other way around. And for knots, we usually want that thing, but turns out we usually only get that thing. So we somehow end up with invariants of framed knots in this setting. Don't worry about what framing is. For now, we'll just focus on the middle one, the ribbon, because it's slightly nicer to explain. Okay, so we have these 3 things. The standard Reidemeister 1, the ribbon, and the framed Reidemeister 1. Okay, and they come up naturally, and they imply one another going in this direction, but they don't apply one another going in that direction. Did I say it the other way around before? Also, let me make this clear. So this direction works. So that direction doesn't work. Of course, if you have the Reidemeister 1 move, then you get the framed Reidemeister 1 move, for example, but not the other way around. Okay. And the reason why I want to so they're really different, right? So you can cook up examples where one of them holds, but not the other. And the reason why the middle one is so interesting from the point of view of topology, the third one is also interesting. The first one is just knots. The third one is also interesting, a bit more difficult. This one is really nice because you just think of, instead of a knot, you actually have a band, a ribbon or a belt. And the belt is such a thing, so it has a little bit of thickness. And this can do something different than an arbitrary thin strand, which usually we think of as a knot. Because if you do this twist, this is my Reidemeister move, and you really pull your hands on both sides and stretch it out, it is not the identity. It does this little twist thing, right? It curls over. So here, essentially this belt has two sides. One of them is this dark greenish color, and one of them is this light color. So the other side will show over, right? It twists over, and the other side will just show. And interestingly, our topological invariants that we cook up from categories can actually detect this. So this is a slight subtlety that an arbitrary thin strand will not do, but a real strand with a thickness and two sides, like your belt or a ribbon, that will actually do this. And because these are ribbons, this is why this is called the ribbon equation and ribbon categories. That's literally what we're going to do, right? So the distinguished here is, well, essentially there is now a little bit more subtle topology going on, where something can just flip over on the other side. Interestingly, this is, algebraically speaking, the more natural equation than this one. So somehow ribbons come out more natural than knots for some reasons. This one is always true. It's kind of a little bit boring, and it's related to framing. Going to do that eventually, but not now. And there's also, you can just prove it. It just comes from the structure of a braided pivotal category. So what you need to do, I think, or what people usually do, and I feel like what I mean by I think is I feel like this is pretty natural. So if you can get this one for free, and this one has such a nice topology, and this is the one you really want in the end, knots, maybe you should give the middle one an extra name, right? So whenever the ribbon equation holds, and you will call that a ribbon category, for the obvious reason that it is a ribbon. So literally this is what I have in mind. A ribbon category is a braided pivotal category satisfying the ribbon equation. And this gives us not invariants, but it really gives us invariants of ribbons and not knots. But anyway, and ribbon categories are usually the algebraic objects we like to study. I'm going to, in more details, how to construct such categories later on, but this is kind of the picture I have in mind. So here, I literally build a figure 8 knot out of a ribbon type thing. So it has a front and a back, right? It has a black and a white face, and this is the type of object we really study. So ribbon knots, if you want. So it kind of turns out that these appear naturally in the setting of algebra for some reasons that we are going to see in future videos. Anyway, I hope you enjoyed this video, and I also hope to see you next time.